Hello and welcome to another episode of Twimmel Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Once again, the recording you're about to hear is part of a series of interviews I recorded live from the O'Reilly AI and Strata conferences in New York City. My guest this time is Francisco Weber, who is the founder and general manager of artificial intelligence startup Cortical.io. Francisco's presentation at O'Reilly AI was called AI is not a matter of strength, but of intelligence. To set the stage for my conversation with Francisco, recall that in the last interview, Pascal Fung noted how recent advances in natural language understanding have been based largely on ignoring language structure and focusing on statistics. Well, in this interview, you'll hear Francisco argue that the next advance in NLU will come from shifting our attention from statistical models to models based on a more sophisticated model of the brain. A warning in advance, this conversation is very technical and moreover, rather abstract. Don't be afraid to listen to it a couple of times to allow the ideas an opportunity to sink in. You'll find this week's show notes at twimmelai.com/talk/10. You might be particularly interested in a link to Francisco's presentation slides, which are helpful to review alongside the podcast. And now, on to the show. Hello, everyone, here at the O'Reilly AI conference, and I am with Francisco Weber, who gave a great talk earlier on AI is not a matter of strength, but of intelligence. So welcome, Francisco.
Hello. Great to be here and to talk about my talk, actually.
Nice. Why don't we start out by learning a little bit more about you and hearing a bit about your background?
Yeah, so I'm coming from the natural sciences. I'm trained in medicine in Vienna, but I have since ever sort of a built-in affinity to technology and ended up going into the natural language processing information retrieval domain, where I'm in for like 20 years now about. I've been, so Cortical.io is actually my third company. I previously worked in the field of patent information, which is also a sort of complex natural language issue. And that was basically where I learned of the limitations of the current systems. And that motivated me to actually try and find something substantially different.
Okay. So tell us a little bit about Cortical.
So Cortical is all about two things, in fact. So one thing is a theoretical framework that we have discovered, I would say, and that we explore, that is about how the human brain, to be more specific, actually, the neocortex supposedly handles language information. And the other is that we basically use this theoretical framework to also create a real technology that we basically offer to the markets. Currently, this is mainly for enterprise customers. They have a lot of problems out there, and so to say the effort to revenue ratio makes us work there for a while. But we do also have a public API where basically everybody can play around with our technology for free. So that's what the company sort of does. And we try to find a really alternative way to deep learning and to the more traditional ways of statistical modeling and machine learning. For the moment, our approach doesn't actually use any statistics, so which might not be the case in the future. So there are some motivations to maybe team this up with deep neural networks or so. But in fact, it's not our specialty, so I leave this to others to try out. What we basically do is that we have solved, I would say, or we have found a solution to the famous representational problem that exists in natural language understanding since decades. Basically, a very fundamental issue is that basically says if you find out how to represent language, which means text at some point, in a way that you can actually compute with it, then many of the big problems like ambiguity, like vocabulary mismatch, all the traditional problems we have in NLU basically are solved in one approach, and that's what I actually presented today. Is that by this little shift in how to generate the features, everything falls in place afterwards in a very convenient and most importantly efficient manner. Yeah.
So tell us about this shift.
Yeah, so our approach basically is founded on the work of Jeff Hawkins, who is a researcher in the area of cortical processing. So he works on finding out how the human neocortex actually processes data. I say data in general because one of his findings was that regardless what kind of data, so might it be hearing or seeing or touching, all of that data when it comes to the neocortex looks the same. It has the same format, which is what is called a sparse distributed representation. So it's like a large vector of binary features. Where you have like 2 to 5% of those features are actually set to 1 and all the rest is 0. And everything is encoded into such an SDR. And that was basically our first goal, is to find a systematic, unsupervised, because otherwise it's not doable in practice, a systematic, unsupervised way of converting text into such an SDR.
Okay. Now, I've heard a couple of times, even at this event, there were a couple of comments that were made. That one of them was, even I think in the keynotes this morning, there was a comment about how, what we've got with neural nets don't have the complexity and the nuance available to express what's actually happening in the brain. And in another talk, the kind of follow-on statement was, so therefore we shouldn't try. We should just use these as tools. And now it sounds like you have a totally different belief system around this.
Well, I mean, fundamentally, what we use as neurons nowadays has, in fact, very little to do with real neurons. Yeah?
Right.
So it was an abstraction that was made like 30, 40 years ago,
yep.
Compared to today, on a very rudimentary understanding of what neurons actually do. Mm-hmm. Nowadays, we know more. We know that, for example, the actual learning happens through the building and unbuilding of synapses between them. If you actually model a neuron, not chemically, so it's not about sort of creating all the molecules that are there, right, because that's something that nature uses. Yeah, so nature, in evolution, you always have the components from the previous evolutionary state, and you have to play with this kind of Lego bricks and do something, which sometimes looks a bit inefficient. But what is key on the other side is what is the mechanism that those real neurons create, and that is what Jeff Hawkins actually has figured out and is about to even figure out in more detail.
Okay.
And so certain aspects like the sparse binary representation are actually key for this to work properly. And by working on text, so our approach was basically, okay, if Jeff is right with his theory, everything he says about the general way how the cortex processes has also to be true for language, as the language is generated by the cortex too. Mm-hmm. And so we basically took his theoretical framework as a set of constraints, and we try to say, okay, if that is the limitation, how can I put everything I know about language within this limitation? Mm-hmm. And it took a while, actually 25 years or so, in general. I mean, I know Jeff's work since a little bit over 10 years, but everything that was sort of needed, to me at least, to sort of understand and to operate at this abstraction level took a while. But then I had at some point, while I was listening to his talks, reading his book on intelligence and so, and it was literally sort of taking a shower, and in a second I had this visual idea, so to say, how this could happen. Okay. Because it boils down to a sort of visual aspect, in the sense that as a necessity, we have to find a representation where two words that mean similar things have to actually look similar. And when I say look, their SDRs have to be similar and literally similar. So in fact, and that's also what the brain is doing, to put one word representation on top of the other word representation. And by measuring the overlap, how many of the bits actually stay at the same position, you get two things. One is how related are those words? And the second is by looking where the overlap happens within this representation, because this is a two-dimensional, it's like a bitmap with 128 times 128 pixels. Okay. And like 2% of those 16,000 bits are set to 1, therefore are like pixels, dark pixels, if you want. Okay. And so it's actually a visual thing. And you can try this out on our website. When you take two words that are sort of have a common context or so, you can actually literally see that they look similar. Yeah. And interestingly, I mean, it's hard to, or maybe even impossible to absolutely decode what it means. But if you, as I have done, stare a lot into these representations, you end up seeing the differences like in a blink of an eye. Yeah, you might not know the details, but to identify that two words are similar in this representation takes a millisecond. Yeah, and that is already a hint, so to say, that shows what the major gain is of this approach, which is efficiency. Yeah, and that's what our brain is famous for. So I know that on the deep learning, in the deep learning community, things like precision and so are the key metrics. Right. And they are, of course, important. It's like having glasses that are blurry. Yeah? Nevertheless, at the very end, the choice of algorithm is not so much on the precision, but it relates to down-to-earth energy efficiency. Yeah, I mean, the brain works with something like 10 watts or something. So I don't even want to know how much power the GPU servers eat up. And that is already a very good hint of how well a certain approach is. Yeah, and that's why I chose the title also of brute force, because statistics, especially if you do statistics of large combinatorial spaces like language. I mean, you basically can create an indefinite number of combinations of words to make meaningful sentences. So to do statistics on such an open system, it's a real hard work because you have to provide endless examples to have like a microbit of semantic payload in your representation. Yeah, and it works up to a certain point, no question. I mean, the statistical systems work, but what you see is that in order to make the model a little bit smaller or to gain a tenth of a % in precision, you have to put a lot of effort in. Yeah, so to get from 60 to 61% precision, you might even double the effort. Like going from 1 to 60 is the same as from 60 to 61. Yeah.
If I could drag you back a little bit, it sounds like understanding the Jeff Hawkins stuff is important to understanding what you guys are doing to some degree.
Yes, definitely.
So he's defined this sparse data representation, this SDR, and is there also a different concept of a neuron that underlies that?
Absolutely. So he's modeling a real neuron, but on the functional level. So he's also modeling a neuron, if you want, but he's modeling everything that is relevant within the neuron for processing data is part of his model. And everything that might be housekeeping, building up proteins and stuff like that is not part of the actual data processing layer and therefore not represented there. So he's basically tried to expand the simplistic concept of a neural net neuron to become a real neuron. And sometimes if you face the problem the way it is, the solution is much easier to understand. Yeah? Because it's basically a model-based approach versus a model-free approach. To sort of bring it into one sentence. Yeah.
And so on this base of this more robust model of a neuron, there's this notion of the SDR, which is capturing, when I think of a neuron, I think of, there's state plus action, right? And so this is capturing state.
There's even more. It's state, action, and time. And that is key to what Jeff is doing. Because his networks have time built in. So it's not only of deciphering a pattern of input bits, but it's rather memorizing a sequence of patterns. Because in reality, things are interconnected, so to say. They have a semantics built into the system, everything. And therefore, it is highly improbable, if not impossible, that by having an initial state A, you can predict which are the, let's say, physical possible next steps. And that's what the processing relays on. Yeah, the fact that not like in statistics, after state A, any state could happen, because I need to do the statistics for it. But the reality is that after a step A, there is a certain set of steps which have all to be possible in reality. And what we learn as walking brains, if you want, is what are those potentials, what are the potential outcomes, and how many hints from the initial state could point me to the right next state. And that's, in the end, what the brain is doing. Yeah, the brain is nothing more than a sequence learning engine that does prediction based on what it has seen so far. And if you think through that on a, let's say, philosophical level, you will find out that you basically can solve or explain everything we do that basically follows this basic computation. Yeah. So there are two interesting aspects to this. One is there is no processor. So the brain does this by being a memory system, which is interesting. I mean, in computers, it's exactly the other way around. Yeah? The processing happens in the processor, and the RAM is just a dormant store. Yeah? And the brain obviously does this differently. And the other aspect is that the prediction is in fact the condensed intelligence, because the more I'm right in predicting, the more I'm intelligent. And by the way, I mean, there have been very behavioral ways of looking at intelligence. That's the reason why the dog looks intelligent to the dog owner, because the dog owner knows the dog and knows what predictions the dog is making about things and is right in doing so. And therefore, the dog indirectly, so to say, looks more intelligent to the owner than to everybody else. Yeah. Yeah.
So does the SDR capture all of that, or just the state?
So the SDR is all about getting an explicit representation of the state. So that's the other difference. In the world of brains and SDRs, you only work with what is called semantically grounded information. So every bit in representation of the SDR actually corresponds to something real and concrete. So for the visual system, it's pretty easy because in the end, every bit of the image that is produced on the retina, if you have two dots that are close to each other and have the same color or nearly the same color, you are probably right in guessing that they are part of the same item in the physical world. Yeah? If you have now a representation that gives you the same phenomenon, namely that two bits that are set to one stay close to each other, it's easy to guess that they are related and they are part of the same, maybe subunit of the system. The only thing you have to be sure is that the data that is provided is actually inherently semantic. So it has to be part of a system on a very abstract level. Yeah? So the world is a system, therefore any data that I can hear or see or so about the world is semantic because there are rules of physics, rules of biology, and so on. And the same thing is true for language. Language is data that is inherently tied together by a framework of grammar, of syntax, and all these aspects we know since a long time. But we had the problem on how to actually store these mechanisms. And the reality is, don't store the mechanism, but just store the examples, just store the detailed information, the explicit information.
And are those words or are those?
So in our approach, we declare the semantic atoms in language to be words. I mean, there are like smaller units, like phonemes, for example,
right,
but they have no meaning by themselves. So the first time you actually have a meaning is when you have a word. Yeah? And all the subsequent meaning of a sentence, of a paragraph, a document, an utterance even, comes out of the sequence of those words. Yeah? And so what we do is basically we convert every single word into such a sparse representation. We call this, because it's so hard to say, we call this a semantic fingerprint.
Okay.
And the interesting thing is that through the way how we convert the semantic fingerprint, you take advantage of some of the properties that are inherent of sparse binary vectors. For example, you can make a union of as many sparse vectors as you want, and you don't lose information. Yeah? You can always say from an unseen vector if it was part of the union or not. If you try to do the same thing with a dense representation, let's say the ASCII encoding, you have 8 bits and every possible combination corresponds to another character. If you make a union of a couple of them, no way to say what was the initial part. Yeah? And as I said, the generation of this pattern is done in a way that every single pixel of our fingerprints correspond to an explicit learned context. And you can, in fact...
not a word, a context.
It's a context, which is basically, technically, it's a bag of words, if you want. It's a bag of words of utterances in which the word occurred.
And so what's the scope of an SDR in this model? Is it at the level of a corpus, at the level of a language, at the level of an utterance? Well, not an utterance, because an utterance...
In fact, all of that. So what we do is, in principle, we generate the atoms, which is a fingerprint for a word. But if I want to create a fingerprint for a sentence, I just convert every single word into its fingerprint. I make a stack and aggregate them together. I make an OR of all of them. And then I have, depending on the location on the fingerprint,
you can do this because of this union property.
Exactly. Yeah, that's the reason why we have to stay on the sparse side. Yeah, and if you make, for example, a union of, let's say, 10 words that are in a sentence, you of course fill up the representation. And therefore, after making the union, we do what we call resparsify. We introduce a threshold to cut away everything that fills the fingerprint on more than the 2%. And so we end up with a fingerprint for a sentence that has basically the same topology that is directly comparable to a fingerprint of a word. And we can do this with a sentence, with a paragraph, with a book. Yeah, of course.
Does the SDR for book or for whatever, let's say a book, is it n dimensionality where n is the number of unique words in the book?
No. So there is the topology, and there is, that's the name why we call it semantic folding. There is this semantic space folded into the representation. So the way how we do this, how we generate the word SDRs, is that we take a collection of documents, which are the reference documents. That's, for a human, that would be everything you ever read and heard. Yeah, all language elements that you got exposed to, and we digest them, and we do this, of course, using machine learning, because we are not like humans. We have not the time to wait 20 years or so. So that's, in fact, where we apply machine learning. And what we do is that we, first of all, cut the training material in little pieces, and then we define the size of our fingerprint, which is a metric space, so there is no dimensionality, if you want. It's a two-dimensional metric space, and we position all of our training snippets on this space in a very simple rule. Two snippets that are similar stay close together, and two snippets that are different stay far apart from each other. And then it's, one of these classical iterative algorithms, similar to Hebbian learning, a bit like this local inhibition mechanism. And what you end up with is that you have all snippets about animals in one region, all snippets about family in another region, and so on. And you get a semantic map. And this semantic map is basically used to encode every word, because I can take all the words that are in my training material, and for each of the words, I can say, light up the positions of the snippets where this word occurs in. And then you get this distributed representation. And because you have the folded in semantics, so to say, two similar words like cat and dog look similar if you look them on the semantic map representation of the fingerprint.
Mm-hmm. So you mentioned earlier you gave an example of a 128 by 128 matrix. At that size matrix, like, what are you able to represent? Like, is that a book, all of the books I've ever read, or?
So what it actually represents is a semantic space. Because it's the fundamental of the representation. And if you just do the math of selecting 300 bits, which is about close to 5% of 16,000 bits, the number of combinations you can do is like the number of stars in the Milky Way. So it's a huge combinatorial space. And as you know, we have not the same assumption as in statistics that in principle every word could be combined to every other word. Yeah, so that's one of the central simplification methods, is to say in the language statistics that every word is independent, which is absolutely not true. Yeah, if you have on the semantic level a certain set of adjectives that you associate to a certain noun. Yeah, so there is semantic sort of glue between everything, and in reality that shrinks the combinatorial space, and that's precisely what we need to learn the semantics of it. Yeah?
Mm-hmm. Okay. So this there are elements of this that remind me of Word2Vec. Like, are there parallels that
it's a natural development that we have started NLP and information retrieval with so-called document vectors. Everything was sort of derived from a document, and we found out over the years that word vectors, the representation of individual words, seems to be more appropriate. Nevertheless, there is a fundamental but crucial difference. So Word2Vec, like other word embedding mechanisms, they try to do dimensionality reduction, and they end up with a dense vector. And to put even more on it, a dense vector of double or float numbers, so sort of computationally expensive representations. We don't do a dimensionality reduction. We might even do an increased dimensionality at some point, if you want. But we make it a sparse representation. So we have sparse binary vectors versus dense floating point or the double vectors, which already sort of gives you a hint on where the efficiency will be. Yeah?
Right. So have we got to what you talked about in your talk, or has this all been background?
Yeah, so talk? I mean, I was talking
because my head already hurts.
I understand. I mean, especially because you are listening to this without any visual support, and this is a very visual thing. Yeah. So typically, when I show this and people see the fingerprints on the screen and how they interact and how they overlap, you can see in their faces, I understand this. Yeah. You don't need to know anything about machine learning or so. It's so intuitive, but if I imagine to sort of follow a description that is purely verbal, then you're doing a great job. So the rest basically was that I gave a number of practical examples where we apply this. Okay. And I can cite a few. For example, we do let's say we have certain prototype ways of solving typical problems, and what is the case is that we solve all of them with one unique operator, which is similarity. Yeah, so the only sort of verb we have in our universe is similar or is not similar, and so one thing you can do, of course, is search. Yeah, so you can.
And since you're operating on essentially these sparse vector representations, is when you hear similar, like, is it fair to think geometrically similar,
literally. So we actually measure this by calculating the overlap between two fingerprints, which is the most generic way. I mean, we do offer a number of distance metrics. As I said, this is a metric space, so we have different ways of calculating a distance metrics, like a Euclidean distance and others. But I have to say that, in fact, the pure overlap count is fully sufficient to get the result out of it, and it's very computationally efficient. Yeah. So one of the prototypes, as I said, is search. Imagine you have a collection of documents. You convert each of the documents into a fingerprint. You have a user who types in a language-based query. I'm looking for information about red sport cars. You create a fingerprint of that query, and you just match how much overlap you have between all the documents and the query, and you rank all your documents according to the size of the overlap. Yeah, very generic. It's a real search mechanism. So what you get is really all the balanced aspects that you have in a document. So it's not just does a document contain the word sports car, but it's about the aspects that you might have developed in a document that make it match or less.
And in theory, the document need not even say sports car in it, because you're doing similarity to this conceptual mapping.
Yeah. So it could be the race car, it could be a text about the race car, and my query could be about sport cars, and it would still sort of give a good match. Yeah.
And how does it apply to non-English languages? I didn't hear anything English specific.
Completely independent of languages. So, as I used to say, give me enough dictionaries and encyclopedias in Klingon, and I put you up a Klingon system, no problem. The point is that we have even brought this to a step further, because we were able to not only train in different languages the semantic spaces, but to also topologically align them. And as a result, and I gave the example in my talk, we take the word philosophy in English has a certain representation, and the word philosophie in French has the same representation. So the patterns are the same. And what this means is you could have a system that contains English documents, and you can post French queries, and it would still work, without any translation or anything in between.
Only for those words that have a fair degree of overlap, or?
Well, the words with the same meaning, regardless of the language, have the same fingerprint.
Right.
Yeah?
Right.
So a second prototype where I could give you an example is classification. Mm-hmm. So our classifiers are actually just fingerprints. I don't need to train my classifier. If I say I want to get, let's say, all the tweets about mobile phones, I can take the word mobile phone, create a fingerprint, and then compare the fingerprint of every incoming tweet to my fingerprint of the word mobile phone. And even if it talks about iPhone, it will have sufficient overlap for me to detect it. And even if the tweet is in Chinese, it will be converted into something that I can filter with my English mobile phone fingerprint.
Even if simultaneously in Chinese, because you're fingerprinting that based on its language representation, and there's the similarity is transferable from one to the next.
The Chinese description of the new iPhone generates the same fingerprint as the English description of the new iPhone.
Why is that?
Because
should I be surprised at that? I mean,
yeah, definitely.
That's amazing.
Definitely, you should be surprised. Yes and no. I mean, people who know two languages are able to do this in the same way. Yeah? So there has to be a, let's say, mathematical way of doing this. And the point is that we aligned the two semantic spaces. So we have one topology that we generate in one language, and we can then, with a pure dictionary lookup mechanism, which is the dumbest way of doing a translation, we can convert all the distributed snippets in the vocabulary of the other language and use the same distribution that we have trained with, for example, the English method. And therefore, you have now the convenience to listen, let's say, to the Twitter fire hose, and regardless of what language message comes along, you can filter it with an English example. And I've done that, just to give you a feeling on efficiency, I've done that in real time on the fire hose with my notebook. Yeah, so it was sort of running locally.
I'm trying to run through the... I'm trying to run through the physical analogy or the biological analogy of this. Like, and you know, if the notion here is that you've kind of extracted this model that, you know, more closely represents what's happening in the brain, then and you have this kind of transferability across languages. Is there some, you know, again, we're kind of way beyond, you know, the pale of what's actually going to happen. But like, is there some, like, you take the, you know, some part of the brain from someone who learned Chinese and you transplant it into a person, you know, and then, you know, who has some other part of the brain that is kind of symbolically linked to English, and they could then, you know, translate on the fly, like in theory?
In theory, that would be possible. The truth is that there has been research, for example, comparing the brain patterns of people who have been grown up with two languages. Mm-hmm. They have a sort of speech area in the brain that is actually intricately mixed. Yeah, so the two languages are represented in a mixed fashion, whereas people who have been grown up in one language and who have then learned the other one, they have added a second area, so to say, and that's the reason why a native speaker of two languages can actually easily do translation on the fly, mm-hmm. And can listen or read text in two languages without even noticing that there might be two languages.
Right.
And someone who has just learned another language has always in his head to map from the one region into the other region. Interestingly, there is, and I showed this also in my presentation, there is sort of new research in brain science that supports our representation strongly. So they were able to do an fMRI study, to be precise. So there has been an earlier version of this experiment where people were exposed to words, and then they made like snapshots from their fMRI activity. And what they found out, it was in Carnegie Mellon, if I remember well, what they found out is that you can actually calculate starting with the picture, an fMRI picture, you can say what word this person was hearing when this picture was taken. Yeah, so this is, as you say, wow, but it comes better. And they have sort of trained a machine learning algorithm to make this transfer, to correlate the picture with the word that the persons have been hearing. And the absolutely unbelievable thing is that let's say you have been in the fMRI first. The model has been trained on your images to map to certain terms. If now you present this very same model, the images taken from my brain, it will still recognize the terms properly. And that
independent of whether we speak the same language?
No,
or are we talking about
this has been done in English. Yeah,
okay.
I'm pretty sure that even if I would do this with the Portuguese meaning of your English terms, it still might work out.
Right. But maybe not Chinese.
But why not? The fact is that obviously if two individuals have been grown up sufficiently similar from a cultural point of view. Yeah, so we both went to school for more or less the same time. We more or less read the same stuff. We've heard about the world in the same way. The representation ends up being similar across individuals. And in the end, it makes a lot of sense. I mean, just imagine if we would really be wired completely different from one to each other, it would be very hard to have a simple conversation. Yeah, and in fact, if you do the investigation, for example, I'm pretty sure, again, this is just guessing, but the fMRI pictures from I don't know, some distant tribe living somewhere in the Amazonian jungle, there the overlap between the two representations is probably less because they have just not been exposed to a very similar kind of environment. Yeah, and there is a newer publication which is, I think, it's from this year. I think it's from a lab in the MIT, and there they were actually able to create a map of about 1,000 words on basically nearly the entire cortex, and what it shows is that it's not like every word has a specific position, but every word has a pattern of all sorts of positions all over the cortex that lights up, which is in fact exactly what we are doing with our fingerprints. Yeah? So I claim that we are the first NLP algorithm that gets support by fMRI.
Wow. So this is fascinating stuff. How do you help people make it practical? Like, what if I'm... what are the problems that, hey, if I have this problem, I should be looking at this as a possible approach?
So as I said earlier, we are very strong with this approach in doing similarity calculation and therefore classification. Mm-hmm. And as you might know, in business, natural language processing, nearly all problems can be reduced to one or several classification problems. Okay. So we do all sorts of things. Yeah, I mean, companies who say we want to classify our inbound emails in product requests, complaints, and I don't know, looking for a person, an individual in the company. And believe it or not, I haven't seen any working machine learning solution for that problem out there. I mean, I've been visiting like 150 companies over the last 2 years, of course, trying to sell our stuff.
Right.
But I haven't seen a working solution for simple, I mean, this is really one of the most basic issues you could have. And nearly nobody is actually using technology for that because the statistical approach has a lot of noise that comes in, has false positives, which is, by the way, the biggest problem in business. And we solved this in a couple of weeks. So we make use of the efficiency of the approach in solving this kind of problems within very short time for people.
And so that's a specific use case. Is there like a higher level characterization, like, in terms of problem? Yeah,
so we have customers in the domain. A lot of customers, for example, are in the banking domain. There we solve problems like compliance monitoring, know your customer activities, or automation of business processes that depend on some text input at some point. We have consumer good companies who want to know how to segment their customers, for example. We have manufacturing industry where, for example, in technical products, the documentation, the manual of the product is so complicated. Good example is car industry, for example. A modern car is so complicated that if something breaks, you need to visit the manual or to find out what is this funny light meaning there. Is this dangerous or can I just continue? And people can't find anything because they have the problem that the person in the car doesn't speak the technological language. So an example that I've learned is the query, where do I find a donut? In US, yeah. So I didn't know that before, but obviously the donut is a spare wheel that is sometimes pretty good hidden. So if you look for donut in the manual, you probably don't find it, yeah. And there is a lot of these issues, yeah. I mean, to be even a more extreme case, a person speaking only Spanish, driving a US car and being unable to actually find the right answer, could use our system to sort of pose a Spanish query and be pointed to an English page, for example, and things like that. So, as I said, I mean, in principle, we have solutions all across the domain. We can do things like, for example, you have a LinkedIn profile, you describe yourself in your LinkedIn profile. I can make a fingerprint of your profile. And if I do a fingerprint of my profile, we probably have a lot of overlap as we are interested in the same kind of topics. Traditionally, to make matching of people in HR, for example, you needed to actually, if one person says, I'm expert in G2E, right, and the other person or the job description contains Java Enterprise, there was no way of matching it. Yeah? Yeah. In our case, we match this easily.
Right. Wow. So very fascinating stuff. How can folks learn more, find out more about it, contact you?
So basically on our website, cortical.io, what and you find...
cortical.io.
Exactly. You can go there, you find a white paper where you get basically a more in-depth introduction to the whole approach. You find access to a public REST API that you can play around. It's trained on Wikipedia, on English Wikipedia data. You can then even spin up an instance containing the software on Amazon or Azure to play around if you have more proprietary data or so that you want to use. And of course, you can contact us if you need help to sort of get started. I mean, the problem is that many of us who have been struggling using conventional tooling, sometimes it needs a little bit of help to sort of get the right angle on how to solve something. Yeah. So we do, for example, offer a keyword extraction functionality. You can throw in a text and you get like the 10 most important keywords out of it. Yeah. And I've observed that many people try to systematically extract keywords and then try to do some magic with that. And I just told them, okay, the keywords, you need them if you want to show keywords at some point, but you don't need them to make any computation because you can compare the fingerprints directly. Right. So yeah, there's
a bit of a mind shift,
a change of mindset. Exactly.
Yeah,
exactly.
Right. Well, thanks so much, Francisco. It was great talking to you and amazing learning a little bit about what you guys are up to.
Thanks a lot. Thanks.
Yep,
bye-bye.
Thank you. All right, everyone. That's it for today's show. Please leave a comment on the show notes page at twimlai.com/talk/10 or tweet to me at Sam Charrington or at TwimlAI to discuss this show. Or just reach out and let me know how you liked it. Thanks so much for listening and catch you next time.